Hello again, this is video 4 of chapter 6, video 2 of section 6.2, and we'll start off with an example with seal pups. Small newborn seal pups have a lower chance of survival than the larger ones. Suppose the length of a newborn seal pups follow a normal distribution with mean of 29.5 inches and a standard deviation of 1.2 inches. What is the probability that a randomly selected newborn seal pup is shorter than 28 inches? Alright, so first of all, we have to standardize this. And so to standardize this, well, we know that mu is 29.5. Our sigma, standard deviation, is 1.2. And what we're looking for is less than 28. So our x is 28, and remember that our z-score is z equals x minus mu divided by sigma. Well, we have everything here, so 28 minus 29.5 divided by 1.2. That equals negative 1.5 divided by 1.2. And then, so what's negative 1.5? So negative 1.5 divided by 1.2, and that is negative 1.25. So how do we find the area to the left of this z-score? Okay, well, we have this, the standard normal distribution table. So we're looking for a z-score of negative 1.25, and so here's negative 1.2, negative 1.20 to 1.21, keep going, and this is it right here. So we can assume that about 11% of newborn seal pups weigh less than 28 pounds. So, according to table, approximately, or about 11% of newborn seal pups weigh less than 28 inches. So what if we wanted to figure out how many were born less than 32 inches? Well, we have this formula, so copy and paste it. And so we know so using this formula again, we have an x of 32 minus 29.5 divided by 1.2. So 32 minus 29.5 is 2.5 divided by 1.2, and that equals, let's find out, 2.5 divided by 1.2, that equals 2.08. Since I'm rounding it up to 2 decimal places because our z-score table, if you look, doesn't go past, actually, yeah, it doesn't go past 2 decimal points. Alright. We need this again. So we're concerned with 2.08 So this is the left side of the table, the negatives, and then the second page is the right side. So 2.0, alright, so it's right here. Find the column that has an 8, the 0.8 in it, and there it is, 0.98 or 0.9812. So 98.2% of seal pups are born shorter than 32 inches. But what if I ask the question, how many are born longer than 32 inches? Well, we could plug it into the z-score, but it's the same z-score formula. But since we know this, we can use the complement rule where 100% of the area is under this normal curve. So this entire thing, area is 1. So in this table, we have the area to the left of whatever point. Using the complement rule, 1 minus whatever that point is, we would get the right side of the area. So 1 minus 0.982, what does that equal? That equals 0.018. So about 1.8% of seal pups are born longer than 32 inches. So you can see the work here. That's what I did for the 28 inches. And then this is a less detailed version of finding the less than 32 inches. And then this is the z-score, or the standardized table. And then this is just the shading to the right of 32 inches. So we found the z-score already. All we have to do is 1 minus whatever that is, which we did on the Word document right here. And that's exactly what we got. Yep. So, what if we wanted to find that we randomly selected a pup between 27, so we wanted to find the probability that a randomly selected pup will be between 27 inches and 31 inches. So I would like for you to draw a picture and shade the part that pertains to that question, but I'll find this, and I want you to find the z-scores, but then I can talk you through the problem after you find the z-scores and whatever we need. So figuring out that solution on our PowerPoint, so we have our z-score formula, which is right here. Z equals x minus mu divided by sigma. Well, we know that our mu is still 29.5 because we're dealing with the same data. Our standard deviation is 1.2. However, our x has changed because we're looking for between 27 and 31. And so I'll find the z-scores and then I'll draw it on paint. So we know the formula, x minus mu divided by sigma again, and sigma, or mu is 29.5 divided by sigma 1.2, and so negative 2.5 on the top divided by 1.2. And we have negative 2.0833, but we're going to round it to negative 2.08. How about 31 inches? So 31 minus 29.5 divided by 1.2. Well, this is equal to 1.5 divided by 1.2. And that's equal to 1.25. So now I'm going to draw it. Hopefully, kind of well. So let's just say we have our normal curve. Our normal curve like this. So, and we're assuming that this is a standard normal, and we have negative 2.08, and I'm going to draw that right about here. Negative 2.08, and then 1.25. That might be a little too far out. Let's go right here, 1.25. Don't forget to draw your y or x-axis. The area we're looking for is between these two points, shaded in red. So how do we find that area? Well, we just go back to our standard normal distribution table. So 1.25, that's the high end, so that's that one is 0.8944. So let me write this down. Probability of 27 less than x, which is less than 31, which is between 27 and 31. And we know that's probability of x less than 31 minus the probability of 27, or x is less than 27. So back to our table again, 1.25, right there, 0.8944. So that's what this one is, subtracted by the x is less than 27, and that corresponds with this z-score, the negative 2.08. And that's this, 0.0188. Using our calculator, we can find out that 0.8994 minus 0.0188, well, that's just equal to 0.8806. So we can conclude that 88.06% of sealed pups born have a length between 27 and 31 inches. So here's the shading. I just did the standardized version of the normal table, but if you use the actual x's, that's fine. But just remember that using the z-score formula standardizes it. So here's the z-scores for both of them, and we got the same exact thing. So, and we got that too, 87. Ooh. Yeah, I think that one's off. Yeah, I think this one's off. Ooh. Correction. Yeah, I must have plugged that into the calculator wrong. It actually, that is the right answer. 0.87556. Sorry about that. So, I would like for you guys to work on this example A, B, and C by yourselves, and I'll talk you through it after you pause the video. Alright, so we wanted to find the study reported that the length of a pregnancy from conception to birth is approximately normal, with mean mu equals 272 days and standard deviation of sigma equals 9 days. What proportion of pregnancies last less than 259 days? So, z-score for 259, remember this is the z-score formula. So 259 minus 272, that equals 13, negative 13 over 9, and that equals, so that's a z-score of negative 1.44. Going back to the table, which I can show you here, negative 1.44, that is this row, this column, that's a proportion that we get. So we can go back to our PowerPoint, and we find that the area to the left of it is 0.0749. So we can conclude that the proportion of pregnancies that last less than 259 days is 0.0749. So the next problem, same thing, same distribution, but we want to find the proportion of pregnancies that are longer than 280 days. So first we got to standardize it. Z equals 280 minus 270 divided by 9, which is 8 divided by 9, which equals this. Well, if we go to our z-score table, or standardized normal table, remember this is the area to the left of it, so subtracting that from 1 equals 0.1867. So we can conclude that the proportion of pregnancies that last longer than 280 days is 0.1867. And then our last problem, between 252 days and 298 days, find the z-scores of both of them. The z-score for 252 is negative 2.22, and the z-score for 298 is 2.89. And remember, this is our x, this is our x, our mu stays the same, our sigma stays the same. So that's equal to the highest point, this whatever corresponds with 2.89 on our z-score table, which is 0.9981. And I'll show you. So right here, 2.90, or 2.89, sorry. Once you get to the higher numbers, there's a smaller difference you can see in between each of the numbers, but this is the 1.9981 subtracted by the z-score of negative 2.22. Let's go over to this half of the table, negative 2.22. That's right here, 0.0132, right there. And you can see that use a calculator, it equals 0.9849. So suppose we wanted to find a value from a normal distribution that has a given z-score. To do this, we solve the standardization formula z equals x minus mu divided by sigma for x. So I'm going to do this in Word for you. So we wanted to find, let's just say, this is just a general formula, converting the z-score formula to just solving for x. So z equals, I'm just going to copy and paste this actually. Alright, so right here, we would multiply both sides by sigma. Darn. Again, multiply both sides by sigma to get rid of this. So what we're left is sigma times z equals x minus mu. Well, how do we isolate x? We add mu to both sides, so plus mu plus mu. So you can see these cancel out, so you're just left with mu plus, now remember, according to, please excuse my dear Aunt Sally PEMDAS, that the multiplication goes first. So sigma times z equals x. So that's how we manipulate the z-score formula into solving for x. And if you have any questions about that, come talk to me during office hours or during class or whatever. So that's the same exact formula that we got. So heights in a group of men are normally distributed with mu, mean, 69 inches, and the standard deviation, sigma equals 3. Find the height whose z-score is 0.6. Well, now that we have this formula, x equals mu plus z times sigma. So we have mu, 69. Our z is 0.6. And our sigma is 3. So this part equals 1.8. 69 plus 1.8 equals 70.8. So we can interpret this by saying that a man that is 70.8 inches tall has a height 0.6 standard deviations above the mean, because that's an interpretation of the z-score, if you remember. So we have been finding areas under the normal curve from given z-scores, but many problems require us to go in the reverse direction. That is, if we are given an area, we need to find a z-score that corresponds to that area. So let's go backwards, finding the x values given a probability. So what is the length of a baby seal that's in the 10th percentile, meaning 10% are to the left of it? That's so baby seals that are born, it's the 10th percentile length. So the newborn seals are normally distributed with mean 29.5 and sigma standard deviation of 1.2 inches. And this is where the baby seals will probably not survive. So newborn seals in the bottom 10th percentile will probably not survive, so we need to figure out where that part is. So we can draw a picture and shade that part that pertains to it, and we could find the z-score where 10%, going back to the table, So here's a little screenshot. Here's the closest to where it gets to 10%, so we just use that one. It might be a little off, but that's alright. So we correspond, that's the z-score of negative 1.28, this row, this column, and that's the shading of it. So this is just the seal pup distribution. This isn't standardized, so these are just all the potential observations you could see. So newborn seals in the bottom 10 percentile will probably not survive, and they have this distribution. So we can also find this by rewriting and solving for x from the z-score formula. So x equals 29.5, that's what mu equals, plus the z-score, which we found on the previous slide, was negative 1.28, and our sigma is 1.2, and that equals 27.964, to be more accurate. Or, never mind, I said that. So, baby seals that have a length of 27.964, that's where the 10th percentile is. So, anything at that length or shorter probably will not survive. So I would like for you to pause the video and figure this one out and see how you do, and I'll walk you through the steps. Alright, so Mensa is an organization whose membership is limited to people whose IQ is in the top 2% of the population. That is definitely not me. So assume that the z-scores, or the scores on the IQ test, are normally distributed with mean mu of 100 and a standard deviation of sigma equaling 15. So what is a minimum score needed to qualify for the membership in Mensa? So we need to figure out 2% in the table. So we look at this and remember that finding these. So first we would have to figure out, so 0.02 equals 1 minus something. To figure out that x, we add, or we subtract 1 to the other side, so that equals negative 0.98 equals negative x. Divide both sides by negative 1, and you get x equals 0.98, 0.98, same thing. So we need to search for that value in the z-score table. So 0.98, it's the closest to this one. This one's only off by 0.0002, while this one's off by 0.003. What's that z-score? It's 2.05. So this is a shading of it. Shows the value of x separating the upper 2% from the lower 98%. So the area is 0.2. Just told you that in the z-score table, or the standard table. So subtract from 1. 98% is on the left of it. So now we have the z-score of 2.05. We can now plug and chug and find for x. And that's this formula, x equals mu plus z times sigma. So our mu of 100 times our z-score, which we found in the table, 2.05, times the standard deviation of 15, and that equals 130.75. So since IQ scores are generally whole numbers, we'll round this to x equals 131. So we figured that out. So the 98th percentile of IQ scores is 131. So that means that 98% of IQ scores are less than that, while 2% are greater than that. So just some steps for finding normal values with the given probability. Sketch a normal curve, label the mean, label the value x to be found, shade it in, and label the given area. If the given area is on the right, you subtract it from 1 to get the area on the left, and then look for it in the body of table A.2 to find the area closest to the given area, and then find the z-score corresponding to that area. And then remember we solve for x and have this formula, x equals mu plus z times sigma. So you might, we talked about this, the 68, 95, 99.7 rule, or the empirical rule. So the area between a z-score of -1 and 1, we can do this, or we know that rule. So we know that this one's 68%, this one's 95%, and 99.7% right here. And if you really want me to work that out, email me or come to my office hours and I can do it for you. But here's just the work, just really simplified and really sped up. So this is what it exactly equals, 68.268%. This one's 95.45%, and then this one's 99.73%. But this is the rule we go by. So from the table, the area below plus 2 is 97.73, and the area below -2, so from here on, is -0.0228. Subtract this from this, and you get this number. So for a unimodal and roughly symmetric distribution, which a normal distribution is, it still follows that same empirical rule, 68, 95, 99.7 rule. And this is just another graph illustrating it. So the empirical rule told us that if a distribution is approximately normal, then about 80 or 68% of the data will fall within 1 standard deviation of the mean. About 95% within 2 standard deviations, and about 99.7 within 3. If the distribution is exactly normal, then these numbers are just the corresponding areas under the normal curve, and the rule is nearly exact. So the distribution of heights of young men is approximately normal with mean 70 and standard deviation 2.5. And I'm going to ask you guys to do this for me. So pause the video. So we're asked to sketch the normal curve with mean 70 and standard deviation 2.5. So it's going to look something like this. Something like this. So our location here, probably should be a little bit lower, is 70. So plus 1 standard deviation of 2.5, 72.5. This one, 67.5. So we want to find between which heights do the middle 99.7%. So knowing that, you can fill in these x's here. So we know that 99.7% of the data falls within like -3 standard deviations and 3 standard deviations. So really, we need to figure out what this area is. because this is -3, this is 3 standard deviations. Well, if we wanted to solve this again, 3 times 2.5, and our x here, or our mu, I should say, is 70, and that equals 3 times 2.5, 70 plus 7.5, and that equals 77.5. So that's our highest point, 77.5. And what's our lowest point? Well, we just changed this with the -3, 70 plus -3 times 2.5, and that equals 70 minus 7.5. That just equals 62.5. Then going back to paint, what was this, 62.5? So that's the x values for the -3 and +3. So what's the middle 68%? Well, I just started filling that in. So we can, let's look for the blue area. So here and here is plus or minus 1 standard deviation. So this is what we're finding. So we just add 2.5 to the mean, 72.5, and then this should be 67.5, not 67 point whatever this is. So that's how you figure out those. And just a reminder, the normal model does not fit all distributions of numerical variables. For example, if we were randomly selecting people who submitted tax returns to the federal government, we cannot use a normal model to find the probability that someone's income is higher than the mean value. Because remember, income distributions are always skewed right, and the normal model won't fit. And statisticians have several ways of checking whether the normal model is a good fit to the population, but the easiest thing for you to do is to make a histogram of your data and see whether it looks unimodal. That's very important, and symmetric. If so, the normal model is likely to be a good one. So that's it for the lecture slides of Chapter 6. There's some guided exercises. I'm going to publish this to Canvas, and I would like for you guys to ask me any questions that you may have on these guided exercises, but I believe that they're pretty good.